Swayam Prabha. Digital India. Educated India.
It is again my privilege to introduce our next speaker for today, Professor Sounaka Mishra. Professor Mishra is a professor in the Department of Mathematics at IIT Madras, a specialist in the field of theoretical computer science and combinatorics. He has dedicated his career to the study of complex algorithms and graph theory. Throughout his academic tenure, Professor Mishra has made significant contributions to the field of approximation algorithms, particularly in solving complex optimization problems. His research is widely respected for bridging the gap between abstract mathematics theory and practical computational applications. We are truly honored to have you with us today, sir. So everyone, please join me in welcoming Professor Sounaka Mishra.
So I have seen that, okay, all these things are little bit high level things. Fine. So many sophisticated programs are there, systems are there, then you are doing so many things. And most of the times you are just running a software and you don't know what the software is really doing. And if I have to write a software, then I should know entirely exactly what is the mathematics they are behind. Okay. So this lecture, I will not go in a high flying way. I'm not passing comment to the previous lectures or future lectures. Okay. I'll try to explain to you how do you write a program, very simple program, with your mathematical background. Fine. So software you can write, no problem. Anybody can write a software and they can make a package and give some input, you will give some output. But at the end, once you get the output, what is the guarantee that this output that I am getting is meaningful to my problem? That's more important. That is given a reasonably well appreciated or something kind of good solution which I can use it in a correct way. Fine, that is more important. The correctness of algorithm is more important. This is one thing. Second thing is that how much time we are. So we are always doing. Actually, I need a larger. Okay, we are doing something called resource bound computation. So we have two resources. Okay, so basically two things we are trying to do. That is called memory or space, and then other is called time. Right. So the memory and space. Okay, we can assume that a lot of space is there, and there are so many problems are there which you cannot bound within a particular space, a fixed amount of space. So memory is always bounded. We cannot assume that my memory or space of computation is infinite. Number one. Time is also bounded. I should do the computation within a fixed time interval. Suppose I wanted to predict what is the climate of August 15th of this year. And if I get the answer on 16th August, it is meaningless. Fine, there is a fixed time interval. Okay. Mathematically, we will say that, okay, I'm killing my time. Okay, I'm not come to my topic. Okay, sorry. You must be knowing about so many things like something called, chessboards, for example. On the further partitions are there. See, I'm going slow. Okay, this is 8 cross 8 mesh. This is called to 64 bits. 64 cells are there. So there was a story saying that somebody has some king was having some problem. Then he announced that whoever can solve my problem, I can give anything, whatever he wants. Some young man solved the problem. Then everybody enjoyed the life in this country. Then the king recalled, he says, that person, okay, you have solved the problem, then you should get awarded. So what do you want? That guy said, okay, I don't want anything. Everybody is happy, fine, that's fine. But then the king insisted on him. So then that fellow said that he gave this maize of 64 cells and he said, okay, you give 1 grain of rice here. Next thing is 2 times of the previous one. Okay, and then fill up it. So the king became very happy. So simple question. Okay. Then he ordered the question to, he has ordered to his ministers that you please try to fulfill this wish. But then the king, the ministers, everybody started calculating everything, and they found that they can go off to the cell number 40 or 45 without consuming any grain, assuming that good monsoon in India, and no rats, no pests are consumed any grain of rice. For 3-4 years, they have to collect everything. Then they can come up to 45 cell kind of thing. So the problem became so intense. So it is actually something called 2 to the power 64 kind of thing. It looks very nice number, cute number, mathematically very nice. But if you want to execute it, then these problems comes like that. Then king, this story says that the king committed suicide. Fine. Storytellers are always like that way. So other questions, problem that you know is called Tower of Hanoi. Okay, so you have 3 spindles. This is spindle 1, spindle 2, spindle 3. You have something concentric discs of different diameter. There are 60 such discs are there. Largest on the bottom, next smaller, smallest on the top. This is the initial configuration. But basically in Hinduism, they said, okay, Narad asked the question to the Brahma or Vishnu that how long these human beings are there in the earth, will continue in the earth. Then he said, okay, this is the initial structure. Okay, you can move one cell, one disc from one part to other part. That's rule number 1. Rule number 2 is that no way you can keep a larger disc over a smaller disc. So these are the only 2 conditions you try to do. And the moment you move this all 60 to the 3rd disc spindle of this thing, this 60 to here in the same form, that will be the end of the nature. This was the story. And if you write a simple program, if you see Google right now, so they will have a program which is hardly 10 to 15 lines, the recursive code. I'll spend time on recursion today. There are recursive code is there, hardly 10 to 15 lines, C programming. And if you run in the system, you don't have a system for that thing to have enough amount of memory for that thing. Okay, forget about the time. Okay, but if you are running in the lab in your laptop, maybe you can use this n. Then you can use n is up to 25 kind of thing. With a lot of difficulty, maybe it will take 1 day time or 2 days time. I think it will say that okay, not enough memory. Fine. So this importance of memory and time, this resource bound computation we are trying to do. Okay, fine. This is high level thing. Okay, fine. Come back to the little bit more basic level. We have so many data over a hard disk or a magnetic tape and everything is there. Extended memory, everything is there. Okay. So so Turing model says that I think previous lectures he was talking about some Turing test or something. This is basically goes to the name Alan Turing. So his way of doing is that he defined a computational device mathematically much before a human being was thinking of a need of a computer or calculator, much before, I think 30-40 years before that thing. He was just trying to say, given a mathematical function, I give some input, I want to get the output. What is the function value? Can I do it mechanically? That's why he has designed something, a machine called Turing machine, Alan Turing. So what he was trying to say, we have an infinite tape. Okay, extendable. There is a this is called transition function. delta. So it acts over something, and then it is basically this transition function. You have some kind of input length. This is input string x is there, and then it starts working. So initially the step head will be much before, just before the sale of the input, and then try to send something, and then try to move the head this way, that way, read, write over that thing. All these things are there. At the end, it gives answer. It writes the answer on the tape. So he was assuming that this tape is infinitely extendable both ends. He was basically assuming that the memory is not a constant. Infinitely memory is there. As long as you want, you can get it. And then he was saying that in each cell, however big, whatever symbol you want to write, you can write that symbol. But then he has assumed that finite number of symbols. Intentional, that's very important. Okay, he was using finite number of symbols. Okay, I don't want to get into that thing. Leave it for them. Okay. So then, this is in the modern way what we are saying, or in this same way what he was saying. This is basically algorithm. This is basically algorithm, that it is just a well-defined sequence of finite symbol statements which we are executing one by one in that order. Then it gives an answer which is meaningful to us. Fine, that's the meaning of the algorithm. Okay. So yeah. So here he was assuming, so the finite number of symbols. Okay. We'll try to make a model of that thing. What is whatever calculator you are observing, or mobile you are observing, computer you are observing, everything based on this model, Turing model. It is an abstract form. Material science, physics, everything comes to how to design the hardware, everything, all are based on this thing. Okay. Anyway, so what you are assuming here, when you are trying to say time, okay, and I have to talk about what is called memory also. I have to talk about. So the memory space, what you are assuming here, something is called a RAM model, random access model. Okay, I'll explain that thing. Okay, so what is saying that, okay, these basic operations, division and comparison. These are the 5 basic operations that we are doing always. Okay, all these operations are done in 1 unit time. Okay, so here we are saying 1 unit of time. We are not saying nanomillisecond, all this thing. We are not saying that thing. Intentionally, we are doing this thing because day by day, this technology is changing, material science is changing, physics people are working so nicely. Then they're saying clock ticks per second of every computer, they are increasing like anything. We wanted to make a sentence today so that it will stay independent of the machine. Yes.
Sir, during the tape model, sir, if you assume the tape is infinite, sir, but the number of partitions is finite because the
No. It is.
Yeah, the number of partitions is infinite, but the number of symbols is finite. Right?
Yes.
So then, won't you have to repeat symbols?
Yes, symbols are repeated. Repetitions are allowed. Yes, that is allowed. So yes, this is 1 unit time. All these 5 operations are done in 1 unit of time. That's a theoretical assumption. Because in practice, multiplication and division takes more time than addition and subtraction. Okay, if it takes 1 cycle of time, then addition and multiplication and subtraction almost 6 to 7 times more than that thing. You cannot beat it. We cannot say all are same. This is a theoretical assumption that all are done in 1 unit time. Okay, that's one thing. Second thing we are trying to say, okay, we can store a large integer in a memory. However large integer you imagine doesn't matter, it can be stored in one integer. That's practically not possible. You must have heard about 32-bit register, 64-bit register, all this thing you have this. Okay. Here we are assuming that, okay, this is a theoretical assumption. These are all theoretical assumptions. Okay. Another thing is that unlimited memory. That's also theoretical assumption. You may have 128 GB RAM, hard disk, 1 terabyte, all these things are there. But we are assuming unlimited. Whatever memory is required, we can get it. These are theoretical assumptions. One more is that any can be accessed in one unit time. Okay, suppose what I'm saying that suppose your tape head is here right now, and you want to access some memory location far away from that place. You can access, you can shift this head to that head in 1 unit time. That's the theoretical assumption. So if you, the computer science people, you will talk with this thing that if you are running a very large program and your memory is in a memory tape, suppose one memory cell you are accessing in the first part of the tape, and next moment you are accessing the end part of the tape has to unwind. That takes a lot of time. Okay, that is called page faulting in the computer science people language. But here you are assuming that it does takes 1 unit time. Fine. So these are the major things. Okay. Over these things, we'll try to see. We have an algorithm for some particular problem. Okay. Under this machine, we are running a program with particular input. It has an input. Then we say input length is how many bits is using in the input length. Okay. I'll give the example after some time. Okay. Input length is there. How many basic operations it is doing, this algorithm is doing, in worst case, to get the answer. That's called the running time of this algorithm. I'll give that example, enter next 2 lectures maybe. Fine, I have lost around 10-15 minutes already. Fine. This is, okay, fine. What is a simple problem that we want to discuss for next 1.5 hours is this thing. So this is called, we'll try to work it out something called this we'll try to spend a lot of time, okay, with some example. So one basic example is that, one serious problem is that how do I sort the data in a memory location? You are sorting data in such a form such that I can access it very easily. So simple mathematical problem is sorting n integers. So we will assume that what is called array. Do you know what is called array?
It's a collection of take a list of things.
Sorry. Some people are saying collection of cells.
Sequences of rows and columns which stores particular data types.
Little bit more accurate. Okay.
It's a collection of data values that may or may not be structured.
Why may not be structured?
It's just an
Now, what do you mean by array basically? It is a collection of data you are asking, so in C programming, if you are defining that in C programming, if you are trying to give a command like this thing in the program, what does it mean?
Your 30th index of the array.
Sorry, I have not done the programming for a long time. Okay. Basically, what is the understanding is here is that you are asking the system, compiler, you are asking the system through compiler, C compiler, that you give me 30 memory locations contiguously. Each memory location is of integer type. Contiguous memory locations. Okay, in the memory, wherever is there memory, hard disk is there, you give me contiguous 30 memory locations. Each one is of integer type. Suppose you say float. 30 contiguous memory locations. Each one is of type float or real numbers where you can store. Okay, so contiguous memory location. Okay, this is the array. So if you are saying contiguous memory location array A, maybe C programming starts from 0 to 29. Okay, I will use in my arguments from 1 to n. I will use after some time. I will get out of the C programming actually. Okay. So here, this is 30 memory location contiguously given to you, the system is giving to you, and there you can access 15th location in 1 unit time. So the assumption that okay, any memory cell can be addressed in 1 unit time, this thing is somehow we are successful in the compiler design only up to extent of array. But if you take a very large array, maybe 10 lakhs contiguous memory locations or 10 lakhs or maybe 10 crores, then it may be violated a little bit. But the system says that okay, ith location I can get in 1 unit time. That's the assumption that okay, in array somehow supports that thing. Okay. Now what I'm assuming that okay, I have given an array of n integers. Okay. Basically I'm writing as A1, A2, An. These are given in some array. The first element is A1, second one A2, like this thing. Maybe for example, if you say 15, 30, 25, 7, like this thing. These are not sorted. Okay. So aim is to do, can I do it in the I wanted to convert into a sorted array by spending some time. Okay. And this running time should be in time some function of n. Okay. N numbers are given to you. I wanted to do this thing. So what is this function? What are the algorithms you know for sorting n integers?
Are you talking about sorting techniques?
Yes.
Bubble
Bubble sort, okay. Insertion sort, okay. So forget about insertion sort, okay. Let us do bubble sort. Why it is called bubble sort?
last
We'll come back to that thing, okay. What is the bubble sort is doing?
you compare like side by side and then swap if necessary, then you keep on doing every activation.
Okay, so fine. I'll try to kill time here right now, okay. If I'm writing a program, according to my knowledge or my understanding, I believe that, okay, I always say in the classroom that the computer is and it has no intelligence, okay, ideal, highly obedient slave without intelligence. You have to say extremely one by one the statements that you have to execute. That I was trying to say algorithm. Okay, you have to say everything. It doesn't understand what is K, what is N. It doesn't understand anything. You have to give specific sentences, instructions in a very well-defined manner, and it should run in execute in a very within small time interval with memory and space within some control, and at the end it gives some answer, something it writes on the tape, and that tape write-up is meaningful to me. Okay. So if you are looking at this computer is a very, it has no memory, ideal slave, it has no memory, no intelligence, then how do you sort it? Okay. So what you are observing is, okay. So you have 1 to A is memory location, and this is x1, x2, xn, xn minus 1. These are the n integers are given there, and you imagine as if they are some kind of pebbles, metallic spherical objects. Their volume is proportional to their weight, their number. If it is 5, this is a 5 radius volume, 5 unit radius. If it is 10, this is a 10 radius volume, bigger volume. So assume that I am a blind person, I don't have any memory. Fine. And 2 objects I'll hold in my hand. Fine. I'll try to sense which is bigger and which is smaller. So he is looking at the face to the board. Okay. So it was instruction is given that the largest element should come to here. To come here, and smallest should be here. Largest should go this side, smallest should come here. So he will has only 2 hands. He will hold 1 and 2 and compare these 2 things, which is bigger or smaller. He said, okay, your left hand side should be always smaller, right hand side will be bigger. If they are not in the proper order, he will swap them. Fine. He will compare first and second first. If they are in order, fine, don't change it. If they are not in order, he will swap it. Then he will try to have the second and third. Okay. If these 2 are not in order, then he will swap. Otherwise, it will remain as it is. Then 3, 4, 5, 6, 4, 5, 5, 6, like this way he will do. Fine. Okay. That is called fast pass. I am defining a name, terminology there. This is called fast pass of the algorithm. Sorry. This is called, okay. So what is comparing with 1, 2, 2, 3 is comparing, and this thing n minus 1 and he is comparing like this way. First and second, if they are in order, fine, no problem. If they are not in order, he swap them. Okay. Then second, third. Then third, fourth. Okay, let's write down here. Okay. It does like this thing. So this person doesn't have any memory, don't understanding anything, zero understanding, just instruction wise is following. But you are sitting as a organizer or the intelligent character. You have the analyzing capability here. So at the end of this first pass, he came up to this pair and he stopped. So what should be your observation? The largest element comes here. Fine? Is it okay?
So then according to this model, in the middle it can be any other. It's just that the first should be smallest and the last should be largest.
No. Last one should be after this first pass, after doing this many comparisons, basically this comparing these 2 guys. After having these many comparisons, the largest element must be coming into the last position. Wherever the largest element is there, doesn't matter. Because suppose largest element is here. So it is bigger than always. It will come swapping by this, it will come to here. Then second, third, largest is here, it will get swapped. Like that, this largest element, wherever it was there initially, after first pass, it will come to the last element. Fine, that is your analytic capability. That's why natural brains are more powerful than the artificial brain, whatever we are saying. Sorry, computer science people will go against me. That is going against ChatGPT, neural network. Okay, yes, up to some extent they are much faster, but they cannot mimic the human brain. Fine. Okay, so what is the observation is here? After this fast pass, the largest is at A. Fine. With your capability, your understanding or analyzing capability, you could able to prove that the largest element has gone to its right place. Fine. I am using the new phrase called gone to its right place. I will use it afterwards. Fine. And also, if the largest element is somewhere here, actually this was the largest element, it has jumped to several places. Then finally it came to here. The shifting the data is costly. Swapping is 3 to 4 units of steps. Is it okay? Sorry, XY. X is a member location, Y is a member location. We are swapping this data. How do? You create a temporary data, store temporary X to that thing, somewhere X, and then X is equal to Y, and Y is equal to 10. This is 3 steps. Swapping means 3 steps. You have an extra memory location, take the data out from there, then make changes, Y comes to X, then in Y location you put the data in temp. Okay, so the data changes. This is a 3 unit job. Okay, so this is something called 3 steps. Fine. So when the data is jumping from one to another place, I'm doing swapping. So I'm spending some amount of time for that. That's a bit costly for us. Okay, I'll use it, generalize it after some time. So first I'm saying that, okay, the largest element has gone to its right place after the first pass. So then you apply your intelligence, then tell him that guy that don't look at the last thing. Now you work from 1 to n minus 1, do the same thing. Fine. Then this guy will do the same thing. So in the second pass, so he will do, so how many operations are they has done? Okay. He has done n minus 1 comparisons. Okay. So he has done exactly n minus 1 comparisons. Okay. Per comparison, he must have used at most 3 steps. If they are in order, then he is not doing anything. So that is a 0 number of steps. But if they are not in order, then he is spending 3 steps. Computer is doing 3 steps here. This, okay. So let us forget about this swapping cost. Okay. This many comparisons he has done. That is guaranteed. In the second pass, he has up to n minus 1 objects. Okay. So he will do exactly n minus 2 comparisons. Fine. So he will continue like this thing, and he will end up at the last step. How many steps? Okay, he will do only 1 comparison. At the end, he will have only 2 objects, and then he will just set it, and then job is over. Okay, so the number of comparisons that I am counting now, okay, so at this end of this thing, the entire thing is sorted. Is it okay? Fine? Okay, now I am looking for the running time complexity of this algorithm. So how do I write the algorithm? The algorithm will be like this thing that something, okay, and for j is equal to 1 to n minus 1, do something, okay, what you are trying to do, if Aj is greater than Aj plus 1, then you try to swap. Okay, and that's the algorithm.
Shouldn't I and J start from 0?
That's why I'm saying that I will get away from the C program. I said that, okay, array is from first location to nth location. Fine. I'm writing the pseudocode so that you can transfer it to Python or everything. Python is more famous nowadays.
Yes,
Yeah. The snakes move so slow, but Python is too popular. Okay. And so this you are writing the pseudocode so that you can translate into any language. Okay. So, but I am assuming that is first location to nth location. Okay. So this is just simple code for that. I didn't write input and output all this thing, but this is the main mathematics part. And based on that mathematics, you are writing this thing. Okay. So now let us look at the time complexity. Okay. So the total number of comparisons. So total number of comparisons is equal to n minus 1 plus 1, which is equal to half into n into n minus 1. This many comparisons are there. So this is not the total time complexity. Sorry, n minus 1 plus n minus 2 plus this thing up to 2 plus 1. Is it correct? No. How do you do this thing? You know the story behind this thing. Sorry, is it correct or correct? Correct. You know the story behind this thing? No, that is resolved. Now the story behind this equation. In class 3. Yeah. Gauss. No, sorry, what is his name? Forgotten his name. Gauss, yes. Teacher comes there, just enjoying in the classroom, making lot of noise. The teacher came inside. He said he has to give some assignment so that they will take 1 hour time. He said 1 plus 2 plus 3 plus 10,000 something, maybe 300 something. Give the final value. So everybody was busy with 1 by 1, but then this person, Gauss, said, okay, he just wrote in the reverse way. Out of everything is equal to n plus 1. There are n additions. Everything is done 2 times, divided by 2. That's the story. Fine. Okay. So this many comparisons we are doing at any cost. There is no bargain over that thing. Okay. Then per comparison, I said the swapping will take 3 to 4 steps. But it's not for every comparison. Okay. If this sorted array, the input is a sorted array, then there is 0 number of comparisons. Okay. But if it is in some other way, jumbled way, some other way, then the number of comparisons may be more. But if you take the reverse way data, largest in this side, next smallest, and the smallest in this side, and you want to reverse it, then you have to take maximum number of swappings. Keep it in mind. Okay. If it is sorted array, number of swaps is 0 for this algorithm. I am now talking with respect to a specific algorithm and arguing about this thing, that when it will behave very nicely, when it will behave very badly. Fine. I am going too slow. So when we'll have the break, sir? 5 minutes. We'll give a break for 5 minutes. After 5 minutes, okay. Let us finish the bubble set and then we'll come back. Okay. So this is the algorithm is fixed now. Okay. With respect to this fixed algorithm, we are looking for the scenarios on which it will behave extremely good, means less time, and when it will behave extremely bad, worst case scenario. In worst case, how much operation it will take. Fine. The worst case scenario here is that, okay, if I give the reverse way order, input is in the form that largest at the beginning, smallest in this other end, and I want to do it upside down. Then every swap, every comparison, there is a swapping. Fine. So it will take maximum amount of time. In worst case, so I have to erase something. In worst case, this algorithm, bubble sort, will take it will make something like 3 times half into n into n minus 1. Basic steps it will do. This many steps he will do. Fine. So this is equal to 3 by 2 n square minus 3 by 2 n. So this is a polynomial of degree 2, where n is the number of inputs, n integers. Here we are, okay, so how many memory cells initially input is as n locations, okay. So with respect to length n, this algorithm in worst case will do this many operations. This is a quadratic polynomial. Fortunately, we have only 2 terms. It could have one more term, a constant term could have been come up. Okay. So what we have done is, okay, okay, so we'll come back to that thing. Okay. Why it is called bubble sort then? Why it is not called a classroom sort?
Because the large numbers bubble up towards there.
There is a physical interpretation, then philosophical interpretation always comes to picture that what they have done, okay, suppose we have a water tank. Okay, so you release a larger bubble, air bubble, and a smaller air bubble, release at the same time. The larger bubble will get released much faster than this thing will go smaller. It will take more time to get released. So here the data movement is like that way, that the largest element, it will go to its right place much faster way than the smaller elements to get into its right location. Fine. The data movement here is somewhat similar to bubbles movement to the get released in the water tank. That's why it is called bubble sort. Fine. Okay. Now what happens is, okay, we'll see. So I'm saying that my Tn is equal to the number of basic operations made by my algorithm. In worst case. With n number of inputs. Okay. I'm defining some function Tn. I'm defining Tn is that you have defined an algorithm sorting n integers. Okay. How much basic operations you do in worst case. So that's why I was trying to see what is the best case scenario, what is the worst case scenario. Okay, we always try to count the worst case scenario. Right? In worst case, how many operations to do? So for example, this bubble sort, for bubble sort, my Tn is equal to that polynomial, that is 3 by 2 n square minus 3 by 2 n. Fine. What you want to make it easier for our side, that suppose you run a very complicated algorithm, it runs in n to the power 300 and it has a polynomial of 300 terms and these coefficients are more complicated. Keeping in memory and going to other side, after 10 months you give a lecture there somewhere to remembering all this thing, coefficient, 300 coefficients is extremely complicated. It has a different intention also, what I am trying to say, but just one example to you. In order to avoid this thing, this kind of remembering these coefficients, we are using something called asymptotic notation. Okay. Okay. Asymptotic notation. Here we are saying that this is equal to big O of n square. What you are trying to do is that this is a polynomial of degree n. Highest degree coefficient is always positive. What you try to do is that you knock out all the lower degree terms, also remove the coefficient of the highest degree term, you just write it there. Okay. So, for example, if you say my polynomial is something we say my f of n is equal to something like this thing. It can have something very complicated thing here also. Fine. Exponent n to the power something. It can have in a complicated way. So then we are saying that this is big O of n to the power 3.705. Okay, so there is a mathematical definition of these asymptotic notations. Okay, so yes. Okay, fine. So what you are saying that, okay, the bubble sort runs in order of n square time or in quadratic time. Fine. It runs in quadratic time, order of n square time. Okay. Fine. Shall I give Keshav has, Keshav has asked me to give the formal definition of these asymptotic notations. Okay. By the organizer requested me that to give that thing, so I will give it right now. It's a very simple thing. So, what it says that, okay, we'll finish quickly this thing. Okay. Okay. So, f and g are two functions from set of natural numbers to set of natural numbers. Okay. Functions are domain is from set of natural numbers, range is also set of natural numbers. Okay, we are saying that big O of Gn, okay, big O of Gn is actually a collection of functions satisfying certain properties. Basically, is a set. But here we are using abuse of notation that is equal to this thing. Actual thing, it will be very clear after some time that it should be belongs to this thing. So this is equal to set of all functions of f of n such that okay, set of functions of this thing such that there exist positive constants c and n naught such that 0 is less than or equal to f of n is less than or equal to c times g of n for all n greater than or equal to n naught. Mathematics department is horrible for this thing. Fine? No. Plus 2, 12th standard students are there? Some of you are 12th standard. Or 11th standard also? No. All are going to 12, that's fine, 11th class. Fine, after some time we will go to calculus course, limit of a function, continuity of function. There, we always struggle in the IIT system for first semester students for this epsilon delta mathematical formal definition. So here it is more complicated because of, here is a quantifier. There exist positive constants, okay. Mathematically you are writing there exists a two constants. Who has seen those constants? We are not giving formally. We are saying that there exist constants. Fine. And then saying that, okay, there is another quantifier for every n sufficiently large. Okay, what does it interpretation? This is, if you are trying to mock it in this form, it is really complicated. Let us understand what is the interpretation of this thing. Okay. So I have to erase it. Fine. So it says that, so in this thing, n, this is, I am computing f and g in this axis. What's the value? For different values of n, what is the value of f and g? So g, some constant times c of jn, gn, is that this is a function like this thing, some constant times of g of n. Function is moving like this way. As n increases, the function is going like this way. And it is 0 is a positive function, so 0, I have taken something like this way. Okay. When I am looking at the function f of n, it says that it should not exceed this thing for large values of n. Okay, so the function f may, so this is different color is there. So this function may oscillate this thing, but after some time it will go like this thing. Okay, so it says that I can choose my n naught is like this thing. After n naught, for every value is bigger than n naught, this function will never exceed c of gn, c times g of n. But before that thing, it may become smaller, it may behave erratically. But after n naught, this function is always lie below that thing. So these kind of functions are put it in this bag, that is called big O of gn. Okay, so when you are saying that bubble sort algorithm is order of n square, so with random access model, whatever way you do the algorithm, whatever system you are using, advanced system today or after 10 years, maybe 50 years, it will always behave like quadratic. It will behave order of n square. Fine. So there are other notations are there like omega of g of n. This is asymptotic upper bound. This is asymptotic lower bound. So that is written like this thing, f of n, such that there exists positive constants, same thing, c and n naught, such that something similar happens. This is 0 is less than or equal to c of gn is less than or equal to f of n for all n greater than or equal to n naught. For sufficiently large values of n, this will remain as below the f of n.
So what is the upside of this?
Oh, this one. We have just borrowed from logic, shorthand notation. This is there exists for everything. This is universal quantification. This is existential quantification. If you get into mathematical logic after some time. Okay. Yes.
So is this asymptotic analysis only used for functions that are positive, greater than or equal to 0? Because
it is used in many other ways. Okay. For your level right now, I am saying that what I have motivated that I wanted to get rid of these kind of coefficients and lower degree terms. It has many applications in complexity theory, other things. Okay. When people started discussing about this thing, then the pure maths people said, okay, it's a useless thing, you are saying something. But slowly when complexity theory developed, other things theory developed, I said, okay, people are speaking something sensible.
What if the coefficient of lower degree exceeds the...
Yes. suppose kind of thing, very large coefficient. Okay. But if you take much larger n, then this term will dominate. Okay. Whatever large coefficient you take in the lower degree term doesn't matter, but for that things there exists some n naught. So the beyond n naught, this will dominate. So that's the interpretation of n naught. So initially in this part, my function will behave erratically. There's something bigger, something where I have no control. But after sufficiently large n naught, that's a fixed constant. So C and n naught, they are interlinked along with these coefficients. So that's why the math people are saying there exist positive constants. But if you are trying to prove mathematically, you have to find that constants. And C and n naught, they are interlinked in some sense. Is it okay? Fine. And then combinedly, these two things are called theta of Gn. Asymptotically tight bound. It is always sandwiched between two things. Like it will be sandwiched between this is C1, then C2, G of n. After some time, for large values of this thing, the function f of n is sandwiched between these two. It will never exceed that thing, never go below that thing. Fine. So we'll try to stop here. For the we'll go for a break. Motivation for break. After break, what we'll do for motivation? 2-3 lines. Okay. So what you said this thing right now, that the bubble sort algorithm takes quadratic time. Okay. Question comes: is it the best possible thing?
Linear is possible.
You can prove that linear is not possible. Linear is not possible. Linear is possible under certain assumption. So here what you have done, that our assumption is matrix, array A is given. I have the numbers A1, A2 up to An. We didn't assume from where they are coming from. These integers can be very large, very small, no comparison, no assumption of that thing. Linear time is possible when you have assumed that each AIs are coming from a small interval. A very simple extreme case is that suppose this each AI belongs to this interval. Basically everything is 3. Oh, okay, you don't know this. So 3 is less than or equal to AI is less than or equal to 3. This means nothing. Okay. Then everything is equal. Then it's sorted anywhere. Fine. But if you say this is 30, each integer between 3 and 30. In those kind of assumptions, suppose very large integers, you take 10,000 integers. They are coming from the range from 3 to 30. In those kind of assumptions, you can do in linear time. But here, we didn't assume that, okay, in what range they are coming from. Then linear time is not possible. That can be proved. Fine. So what we'll try to see next to after the break, kind of thing that order of n square, we can come down to order of n. We can bring it down to that level. It's slightly different strategy. Fine. We'll see you after the break. Fine. See you then.